I typically joke with others when it comes to the t-test that the t-test is essentially the bread and butter test for data scientists and analysts. It's the signature on your paycheck test. When people ask what I do for work, I tell them the t-test. Not to speak in hyperbole, but the t-test is probably the most important and most frequently utilized tool/methodology that a researcher has in his or her arsenal. In this lecture, we'll discuss the basics of the t-test methodology and how to apply the one sample t-test in RCommander and report the corresponding results of such in APA format. And as always, any code which is featured in this video can be found in the video description below. So the history of the student's t-test. The t-test was conceptually derived by William Gosset in 1908. He was a chemist working for the Guinness Brewing Company in Dublin, Ireland. Student was the moniker which Gosset assumed to publish his findings, as Guinness explicitly forbade its chemists from publishing. Now, the student's t-test is most commonly known as the t-test. The two terms are used interchangeably, and it has three variations: the one sample t-test, the two sample t-test, and the paired t-test. In this lecture, we're only going to be discussing the one sample t-test, and in the subsequent lecture, we'll talk about the two sample t-test and the paired t-test. Appropriate utilization of the t-test. We utilize the t-test when the population standard deviation is unknown. This is almost always the case. When a normal distribution cannot be assumed, and again, this is almost always the case as well. When the current sample size is less than or equal to 30, though even in cases in which the sample size is greater than 30, the t-test is still likely to be the most appropriate method for utilization. A common misconception is that the t-test assumes normality. This is not the case, though the t-distribution does begin to more closely resemble a normal distribution as the degrees of freedom approach 100. So the question is then, why did you learn the normal distribution? Well, the student's t-test methodology was derived as an auxiliary aspect of the normal distribution. Though the student's t-distribution is similar to the normal distribution, that's the underlying distribution which from which the test is powered, the t-distribution allows for greater variation within the observed system. It's more robust. As is demonstrated in the graphic, a greater number of degrees of freedom, more observations, eventually causes the t-distribution curve to more closely resemble a normal distribution. So let's talk a little bit about some of the internal aspects of the t-distribution and its associated methodology. To apply this test, we need to define the following variables. We need the size of the sample, n, the applicable confidence interval and the corresponding alpha. Remember, alpha is typically assumed to be 0.05 with a corresponding confidence interval of 95%. We need the standard deviation of the sample, which is S, the mean of the sample, which is M, and the mean of the population, which is mu. T-test assumptions. We're assuming independence of the observations, which means that each subject should belong to only one group. There's no relationship between the observations in each group. So each sample, each observation belongs to a particular categorical grouping, and there's no interference, no interaction between those groups or between the samples from which each group is comprised. No significant outliers in either group. We're assuming that the data for each group should be approximately normally distributed. And if you need a little bit more in the way of understanding as it relates to bullet point number 3, I would check out lecture 15, the normal distribution, normal versus parametric versus non-parametric, the avian test. It's within this playlist. It's, again, lecture 15 in this Introduction to Statistics playlist. So if you're not completely sure what I mean by the data for each group should be approximately normally distributed, please go ahead and take a look at that video. And finally, homogeneity of variances. The variance of the outcome variable should be equal or about equal in each group. And recall that the Welch's t-test does not make these assumptions. We'll talk about the Welch's t-test in the latter lecture. It's more applicable as it relates to the two-sample t-test. So let's do a one-sample t-test example, and we're going to do this in RCommander, but the fundamentals still apply regardless. So a factory employee believes that the cakes produced within his factory are being manufactured with an excess amount of corn syrup, thus altering the taste. 10 cakes were sampled from the most recent batch and tested for corn syrup composition. Typically, each cake should comprise of 20% corn syrup. Utilizing a 95% confidence interval, remember 1 minus the confidence interval as a decimal, 1 minus 0.95, that's our corresponding alpha value. So we're assuming an alpha value of 0.05, all right? Utilizing a 95% confidence interval, which means an alpha value of 0.05, can we assume that the new batch of cakes contains more than a 20% proportion of corn syrup? So if our data is structured within either a CSV or an Excel workbook, it's going to resemble this image on the right. Of course, this will be your data within the workbook or the CSV, which is in the video description. And these are the samples from which this workbook is comprised. And these are the 10 cake observations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what do we have going on? Well, here are our observations. That's n. Our mean is given to us, which is typically each cake should comprise of 20% corn syrup. So our mean is 0.20. Now that is the mean from which we're going to be comparing the mean of our observations again. So this is the mean that we're comparing the mean of these observations against. And here's our hypothesis symbolically stated. You won't do this for research, but you will do it within the classroom. So this is the symbolic stating of the null hypothesis and the alternative hypothesis as it pertains to this scenario. And it's going to be a one-tailed test to the right because it's more than. So more than means one-tailed test to the right. And we're comparing the mean of the observations to the mean which is given. All right? And when you see it structured like this, when you have a given mean and you're in the classroom, that should set off all the bells and whistles in your head to let you know that you're dealing with a one-sample t-test. So here's how it's done in RCommander. I'll first go through the slides for those of you who have trouble seeing it when I do it on the screen. So we'll go through the slides first, and then I'll do it actually within the RCommander RStudio platform. All right, so you would go to RCommander. Again, we're assuming that the data has already been appropriately imported, and we're assuming that RCommander has already been initiated. So with RCommander initiated, you would go to Statistics, Means, Single Sample T-Test. We then pick the variable within our data set, which we are interested in investigating. So our data set is named cakes, but the variable is also named cakes because this is our variable name here. We're then going to choose this third option. And this third option is indicating that we are utilizing a right-tailed test. All right? We then need to put in the given mean that we're comparing our samples to. That mean was 0.20. So we enter that here. And then since we were using a confidence interval of 0.95 or significance level of 95% or alpha value of 0.05, our confidence level is going to be 0.95. If we were doing a left-tailed test or a right-tailed test or a two-tailed test, these are the options which we would select. In this case, it's a single sample t-test right-tailed. So here is our RCommander output. As you can see, we have the t-value, the degrees of freedom, and the p-value. We also have the mean of the observations contained within our data set. So the mean of the observations, the 10 observations that we had collected ourselves, that mean is 0.289. Now we need one other value, and then we can report our findings in APA format. And that value that we need is the standard deviation. So for that, we go to Statistics, Summaries, Numerical Summaries, Cakes. That's the name of our variable within our data set. And then OK. You're going to get output which resembles what's on the screen now. The only value you're really concerned with is the standard deviation. You'll need that for the APA. Okay. So now I will do this on the screen so you can get an idea of what's going on. Let me get RCommander going. RCommander, there you are. Okay, so here's RCommander. We have our data set cakes. All right. So first we need to get the output for the single sample t-test. So we're going to go to Statistics. We're going to go to Means, single sample t-test. Our null hypothesis mu is 0.2, confidence interval 0.95, and it is a right-tailed test. All that being done, we click OK. And there is our output, and there is the code that RCommander performed from which the output was generated. And now we need to get the standard deviation. And to get that, we're going to go to Statistics. We're going to go to Summaries, and we're going to go to Numerical Summaries, and then Cakes, and then OK. And right here is the output, and here is the standard deviation. So we have everything we needed, or everything we need. So let's get out of RCommander. So let's state our findings. Here's the t-value from the t-test. Here's the degrees of freedom from the t-test, and here's the p-value from the t-test. Here's our null hypothesis. The cakes do not contain corn syrup in excess of 20%. And here's our alternative hypothesis. The cakes contain corn syrup in excess of 20%. Our p-value, 0.002572, is less than our alpha value, which is 0.05. So because the p is lower than our alpha value of 0.05, we reject the null hypothesis, in which case the cakes contain corn syrup in excess of 20%. So we need to write this out in APA format. There was a significant increase of corn syrup within the most recent batch of sample cakes. Mean, this is from the t-test output. Standard deviation, that's from the output which we generated from the active data set step. As compared to the historically assumed mean, that's the mean that was given to us, 0.20. This is the degrees of freedom. This is the t-value to two significant figures. And because our p-value is less than 0.01, we actually say this actually ought to be p is less than 0.01. So p is less than 0.01. Ignore this. It should be p is less than 0.01. That is correct. Not p is less than 0.05. This is the output explained. The t-test statistic which derived by hand would be the sample mean minus the population mean divided by the standard deviation divided by the square root of the size of the sample. And with that t-stat, we obtain the p-value. The p-value is the probability that, given the parameters of the test, that we will obtain a value of equal than or greater than the t region defined within our model. df is degrees of freedom. This value is utilized in conjunction with the confidence interval to define critical t. It is derived by subtracting 1 from the value of n. So here are some hints to remember if you're just joining and weren't following along in the introduction of statistics videos. The null hypothesis is the previous assumption. It's the status quo assumption. The alternative hypothesis is what we receive when we disprove the null hypothesis. We find that the null hypothesis, the status quo assumption, was disproved. The alpha value, aka p threshold value, is always going to be 1 minus the confidence interval. So a 95% confidence interval equates an alpha value of 0.05 or 1 minus 0.95. A 90% confidence interval equates an alpha value of 1 minus 0.90. Remember, if the p is low, the null must go. So here are 3 different test types. And this is applicable whether you're doing a single sample t-test, a paired t-test, or a 2-sample t-test. If we have a 2-tal test, we're testing for substantial change of conditions in either direction. A right-tal test means we're looking for a substantial increase, greater than. That's what we were looking for in our recent example. We were looking to see if the sampled observations were greater than the mean, which we had assumed from prior observations. So it was a right-tailed test. It was a single sample t-test, right-tailed. And a left-tailed test is when we're testing for a substantial decrease as it relates to measured samples within the tested system. So less than, or left-tailed test. So let's see if these are one-tailed, two-tailed, and if they are one-tailed, will they be left or right? A test to discover if the addition of a dilutive ingredient significantly decreases the carrying capacity of steel beams. Well, it significantly decreases, so that's one-tailed left. A test to discover if candy intake significantly alters the behavior of young students. That's two-tailed, because we're looking to see if there's a significant difference, if it's being significantly altered. A test to discover if green tea before bed significantly reduces hours slept. That would be one-tal to the left, because we're looking for a significant reduction. A test to discover if coffee significantly increases hours spent studying. A significant increase is one-tal to the right, because we're looking at greater than. A test to discover if a long morning commute significantly impacts the behavioral scores of workers. That's two-tal, because we're looking for a significant impact. We're not sure if it's going to have a greater than or less than impact. We're just looking for whether or not it's going one direction or the other. So it's a significant impact, two-tal. A test to discover if hours spent on social media significantly impacts mood ratings in teens. Significant impact, two-tal. A test to discover if reading comprehension scores significantly increase as it pertains to hours spent on the internet. Again, increase, significant, increase, one-tailed right. So here is how you would state symbolically the hypothesis tests for a one-sample t-test. The null will always be H subscript O, U equals the mean value. And then depending on whether it's a two-tailed test, a right-tailed test, or a left-tailed test, your alternative hypothesis will be one of these, although your null will remain the same. Two-sample t-test, your null is always going to be this top bullet point, and then whether it's two-tailed, right-tailed, or left-tailed will differ depending on which variation of the two-sample t-test you're running. And the paired t-test, This is your null, and then whether it's two-tailed, right-tailed, or left-tailed, you have to choose whatever is applicable to the variation. So just to bring it on home, there is a one sample t-test, which can either be two-tailed, right-tailed, or left-tailed. There is the two sample t-test, which could either be two-tailed, right-tailed, or left-tailed. And there's the paired t-test, which could either be two-tailed, right-tailed, or left-tailed. And we'll go into each one of these in future lectures. So if you were able to take anything away from this, if this was able to help you out, I would appreciate it if you would consider maybe liking and subscribing, although, you're not required to. It would just be somewhat helpful to me. I hope that this was able to help you out, though, whether it be for your classes or for your research or whatever it may be. If you made it to the end, congratulations, and I hope to see you in our next lecture. Take care. All the best.